All right, so over the next couple of weeks, we're going to cover the last two topics of this course, which include algorithms and algorithm analysis, and then trees and tree-based data structures. Today we're going to start on algorithms and algorithm analysis, and we kind of got a preview of this a while ago when we did linked lists. And I want to go back to that idea and use that as a motivating demonstration. Remember that we implemented this index of method. So what I've done is I've set up a demonstration here where we've got a comparator for integers, so it's just a list of numbers, okay? It's a linked list of numbers. And I've got it set up to insert 1,000 numbers, and it always goes at the start. And so searching for 0 means that you're always going to the end of the list to find what you're looking for. And what I'm going to do is I'm going to time how long this actually takes. So I take a sample of the time at the beginning, then I call that method the index of method. I take the time at the end, and then I divide by 1,000 because it's in milliseconds, etc. And then I report the time. So let me go ahead and run this and show you what it looks like. Done loading data. It was almost instantaneous. Index of 0 is 999, all at the end, right? But it only took 0.005 seconds. Okay. Let's go back. Let's take a look and see and remind ourselves what this code looks like. This is our first attempt, where we the bad painter. We start we keep our paint can at one end of the fence. Always have to go back to the beginning, dip our paintbrush, and then go over to where we were painting. And this is the bad, inefficient version because we have to get the element at index I. So if we have 1,000,000 elements and we're looking at the 500,000th element, that means we have to start all the way at the beginning, traverse 500,000 times just to get that element. The next element, we have to traverse 500,001 times. The next element, 500,002 times, and that all adds up. And that's why it was inefficient. The efficient way of doing this, of course, would be to take your hand with you and keep going along here. Now, what I want, so I've got the inefficient version here. Let's look and see just how inefficient it actually is. So with 1,000 elements, it's no big deal, right? It's really quick, 0.005 seconds. That's not even noticeable on a human time scale. What if I up it to 10,000 though, right? Predict for me how much longer will this take. So it's 10 times as big of a list. So I'm going to have to traverse 10 times as much. That would mean about 0.05 seconds. It's actually going to be even worse. Right? It's what? 20 times as slower? Something like that? Or it's something like that. Of course, these are not exact. What if I go up to 100,000? 10 times slower than this. 0.135 seconds turns into how many seconds? What do you think? A full second? So it was 0.135, right? Don't worry, it'll happen. It is kind of annoying to have to sit here and wait. 15 seconds. Yeah, so that's an order of magnitude how much? It went from 0.14 basically to 14 seconds. That's 100 times as slow. We went up from 10,000 to 100,000. In other words, we only made it 10 times as big, but it was 100 times slower, right? Why is that? So what I'm going to do is I'm going to try to use my iPad here. In the past, it hasn't worked because it's slowed down, but it looks like it's doing really well today. We'll find out. All right. So let's take a look at what it looks like with respect to a linked list, right? Remember, you've got these nodes that are all connected to each other, right? ... And suppose that I want to find the ith, get the ith node, and then however many there are here. There are n nodes all the way to the end, all right? How many operations does it take to get this ith node right here? We have to first start at the first one, traverse once, twice, thrice, ... How many times do I have to traverse a node just to simply get to the ith node? I times, right? So to get the ith node requires I traversals. Right? And if you're searching for something at the very end, right? Or it's an unsuccessful search, in which case you've traversed all of them, and then you've gotten to the end and there's nothing there, right? Then you return -1, I think is what we chose to do, or return null or something like that. Then that's going to require how many traversals, right? Suppose that there are n elements in here, right? In fact, I'll go ahead and write that. Suppose that there are n elements in here. For the first one, I being 1, there's 1 traversal. Right? For the second one, there are 2. For the third one, there are 3. And as you've already observed, for the ith one, there are I traversals. Now, to get all the way to the end, we continue. And to get to the nth one, how many traversals are there? N. What I need to do is I need to sum up all of these traversals. So what is that going to be? Sum running from I equals 1 up to n of I. Now, if you've never seen this before, this is simply just taking 1 plus 2 plus 3 plus 4 plus I plus n. Right? Or put another way, 1 plus 2 plus 3 plus I plus plus n. Right? So, does anybody know a solution to this summation? This is something that you'll just have to commit to memory at some point because it comes up all the time. This goes back to Gauss. This is Gauss's formula. And the I don't think that it's historically accurate at all, but the apocrypha is that Gauss as a child was given a task by his tutor to give him some busy work. So he said, sum up the numbers 1 to 100 and then get back to me an hour later after you've done all this, grunt work. But Gauss, being the child genius, immediately said 5,050. Right? Why? Because in his head, he came up with this following closed form solution for this. N times n minus 1 all over 2. Right? That's Gauss's formula. Right? So let's go ahead and expand this out over here. So n times n minus 1 all over 2, right? I'm going to write this as, a polynomial. A polynomial of what degree? Of degree 2, right? Minus n divided by 2. And then I'll go ahead and include here plus 0. So what is the largest term here? Like we already said that this is a polynomial of degree 2. So if you think about this as a function, right? As n tends towards infinity, n, what is n representing here? What did we start out with? N is representing how many elements there are in the list, right? So n is going to, in this sense, n is going to represent our input size. The size of our list. What is my y-axis here? What are we trying to capture? How many what? How many the number of traversals, or what was I capturing here? Time, as a resource, all right? So time. We'll talk about that in a little bit more detail, but you're right. The elementary operation is what we call it here, is a node traversal. Now, in terms of computation, that translates to time, because to go from one node to another node is going to require a certain number of CPU cycles or a certain amount of actual human time, right? So time is going to be our measurement here. What does this polynomial look like when you graph it? It's going to look something like this. It's not going to be totally accurate here, right? But it looks something like that. What's its growth rate for those of you that have had a little bit of calculus? How do you do that? You take the first derivative. the first derivative of this is going to be some linear function, right? It's actually going to be n, right? N minus some constant. Who cares about constants, right? And in other words, its growth rate is going to be linear. What do we call this function here? When this is the most dominant term here. It's a polynomial degree 2. Another way of calling another name for that would be it is going to be a parabola if you go back over here. Unfortunately, we don't care about that side of the graph. Why? Yeah, exactly. Do we care about negative input size? Can you have a list of -5 elements? Right? No, right? So we don't care about that side. It's definitely a parabola if you looked at both sides. This is, we already said that the first derivative is a linear function. What is this function right here? It's, oops. I don't know how to undo. There we go. This is going to be a quadratic. All right. So, now let's think in general terms. There are going to be some constants sitting out front, right? What we've done is we've basically said that the behavior of this algorithm that we've designed over here is going to be quadratic. In other words, there's some function that captures its rate of growth, that captures how many seconds it's going to take to actually perform the operation, how many CPU cycles it takes, ultimately how many traversals does it take, right? So there's some time function here that is a quadratic function, n squared plus bn plus 0. That's as general and generic as it gets, right? That there is some quadratic here, right? And there's some lower order terms here. Right? Oh, actually, sorry, let me go ahead and get rid of the 0 and make it even more general, some c. Right? Now, if you think about this as a computer, right? The computer, it doesn't just spend time going from one node to the next node to the next node. The Java virtual machine loads up, right? And that's taking some time. So that can be quantified with maybe something down here. It takes 0.005 milliseconds or something like that. There's some quantity down here, and that A and B here are capturing, A and B are capturing how many milliseconds it takes to traverse a node. Do we know how many that is? How many? How many milliseconds does it take to traverse one node to the next? It depends, right? This is a pretty decent computer. I've been asking for a new one because it seems like it's on its last leg. Apple products tend to go down very, very quickly right after Apple Care expires. And so this is about a 5-year-old computer, so 4-year-old computer here. But it's still decently fast. But by fall, the M1s will come out. Well, the M1s for the 16-inch MacBook Pros. And so those are supposed to be blazingly fast, right? Or, you know, put it in terms of a GPU, right? If you do something on a 970, it's okay. If you take that over to 380 Ti, right? Now we're talking much, much quicker, right? A faster computer could traverse the nodes faster. It would take a smaller amount of time to traverse those nodes, but it doesn't matter how slow of a computer you have. It doesn't matter how quick of a computer you have. It still has to traverse 1 million nodes, right? It's just that each node traversal takes a smaller amount of time on a faster computer and a larger amount of time on a slower computer, right? In other words, A, B are constants that depend on your hardware. Upgrade your hardware. Those constants will go down, right? Downgrade your hardware and those constants will go up. But what does not change? What doesn't change is this guy right here, that it's still going to be quadratic. Now let's think about the quadratics in terms of input sizes. Suppose that on an input size of n, right, it takes t seconds to search. Now I'm keeping this general, right? I don't even, because again, I could upgrade my hardware and that would go down, but ultimately the rate of growth would not go down, right? So if it takes, if I have an input size of n and it takes t seconds here, then what if I increase this tenfold? I go from 1,000 to 10,000, or from 10,000 to 100,000, or from 100,000 to 1,000,000. Then how many seconds is it going to take here? Well, remember that this is quantifiable by a quadratic function here. Let's ignore those constants. Let's ignore the lower order term here as well, n. Let's just focus on this n squared right here, okay? So, if it took t seconds before, oops, sorry. If it took t seconds before, and it's quantified by a quadratic, how many seconds does it take now? 100 n squared. And we said that it took t seconds before, so how much slower is it now? 100 times. Sound familiar? What just happened with our demonstration over here? We went from 0.135 seconds to 14 seconds. That's a 100-fold slowing of the performance. Okay? So, what if I were to go predict? What if I were to go up to 1,000,000? 100 times slower. 15 seconds becomes 1,500 seconds. 1,500 seconds is 20-some minutes? 25 minutes? All right. Done loading data, and it's working. We'll go ahead and let it work while we codify everything that what we just talked about, right? So consider searching that linked list method. Our elementary operation is traversing a node in the list, right? For the naive approach, it required about n squared traversals, right? In other words, it is the underlying algorithm. The algorithm in this case was a quadratic algorithm. Right? This is extremely slow. Quadratic algorithms, that is still a polynomial, right? And you'll get theoreticians that say, oh, polynomials are fine. That's all we care about. Well, in the real world, we actually care about things actually running. And so even quadratic is extremely slow. As you can see right here, it's still going. Our prediction is it's going to take about 25 minutes to get this done, right? It's extremely slow. In terms of for every order of magnitude increase in the list size, we have a 100-fold increase in time complexity, right? The time it takes to execute the algorithm, right? Yeah, I'll save the rest of that. All right. So, what's the solution here? Right. I guess I should ask, how bad is this in reality? Right. So the better solution, just to contrast these two things, we're going to let this run here and see how long it actually takes. But the better solution was what? Let me go ahead and go look at the code here. What was the better solution? The painter not leaving the paint can at the beginning of the fence. What did he do? He took it with him. Right? So now let's think about what that looks like. Let's open this back up. Sorry. All right. So let's think about that solution, where we've got a linked list here. ... And say that we go to the ith one. how many traversals does it take to get to the ith one if we take our paint can with us? To search all the way to the end of the list. Start at the first one, go to the next, go to the next, go to the next, dot, 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 all the way to the end. We never traversed it multiple times. So how many traversals do we actually do? We only ever traverse this one once. We only ever traverse this second node once. Only ever traverse this third node once. So how many nodes are there total again? N. So the total number of traversals should be, at most, n. Right? In other words, this is a linear algorithm. And hopefully you recognize it from Computer Science 1. What do we call this algorithm right here? We call it linear search. Right? And this is why we call it linear search. In other words, the time complexity of this one, it can be captured by a linear function. There are still some constants sitting out front here. How many milliseconds does it actually take for you to load that thing up into memory, et cetera, et cetera, et cetera? But again, the highest order term here is all we really care about. Forget about those constants because you upgrade your hardware and those constants change. Right? You take it from a Mac over to a Windows machine, those constants change. Right? What doesn't change is this characterization of the function here that's linear. So what does that look like with respect to the math now? If we had an input size of n and it took t seconds and we increase it tenfold, 10n, then how many seconds does it now take? Just 10 times 10t seconds. Right? In other words, it's 10 times slower instead of 100 times slower. Okay? So we've got the difference between a linear algorithm versus a quadratic algorithm. Right? So let me go back over to my notes here. So the better solution is to take your paint can with you. Right? Only traverse each node at most once. Right? For that one, there are at most one traversals, or there is at most one traversal per node, right? And consequently, the complexity of this algorithm or process is a linear, can be quantified with a linear function. The linear function here being simply just n, right? Again, here I'm ignoring the constants, okay? So again, how bad is this? Well, if we increase the input size by tenfold, then the algorithm will only be 10 times slower. Right? So I'm going to go ahead and open up, let's see, I need to go over here. I've got it on iCloud here somewhere. I've got this figure that I wanted to open up. Here we go, graph. So what's going on in the background here? I already did some math on it before. Basically, it's still running, by the way. It is literally going to take 25 minutes as per our prediction. But what I did is I ran this experiment multiple times. This is the list size. This is n down here. And this is in thousands. So this is 400,000, this is 600,000, all the way up to 1,000, 1,000, and we call them millions, right? So 1 million elements over here. And this is the time that I sampled it. And I ran this a couple of times and took an average or something like that. And you can see the samples here in the blue. What I did is I took a quadratic regression. In other words, I didn't know what those constants A, B, and C were. So I put it into a solver and it spit out what those constants were so that it would give me an actual quadratic function. Then I mapped that quadratic function, which is a nice smooth function, and superimposed it. And you can see that the empirical evidence here, or the empirical time that it took for each one of these experiments, pretty much follows a quadratic function. And by the way, I did try to graph the linear function, but but it's not shown here. Why not? Technically, it is being shown here. There would be no difference between the x-axis or x-axis and the linear function, right? That it stayed pretty much small even with 1 million, and I'll show you that here in a second. So this quadratic function, which you can actually see because it's so bad, versus this linear function that basically stays flat for the entire scale of this graph right here. Okay. So that was 1 million, which is about 600 seconds or so. This is 10 minutes right here. I don't know if it's actually going to be as bad as 25 minutes here, but what did I put in? Was it 1 million? Yep, it was 1 million. But I would expect at least 10 minutes here, 10 to 25 minutes or so. Let's predict this out here. In other words, what if I went even further? Here's the actual number here. I used a quadratic on this particular graph here. I used a quadratic regression that gave me this. Right? These coefficients is what I should say. Right? And this is E. This is very, very small right here, right? And that's what you would expect, because that's capturing how much time does it actually take to traverse from one node to a next. Very, very small with respect to a computer, right? Nanoseconds. A computer can load something up in memory very, very quickly. So these coefficients here are actually quite small. This coefficient is also quite small. There's about 9 seconds of startup or so. It doesn't really matter. And by the way, this has a correlation of 0.994, which is almost perfect. And you can see that when you visualize it. It's almost perfectly, other than a couple of these times here that we have some spikes in the time that it took to execute this thing, it almost follows this, quadratic regression here perfectly. Right? So let's think about this in terms of how long it would take if I made this even bigger. In other words, if I went and changed this to 10 million or 100 million or a billion, right? I'm not going to do that. But using this as a guide, we can go ahead and plug these values in. So 10 million elements. Give me a time scale here. So remember that according to this graph over here, that if we have 1 million elements, it took about, well, let's just bump it up to 10 minutes here. This is 600 seconds, 60 seconds in a minute, so it's about 10 minutes. So if I bump it up to 10 million, that's going to be 100 times slower. 10 minutes times 100 is going to be 1,000 minutes. How much is 1,000 minutes? 17, well, almost a full day. 17.58 hours. Right? What if I went to 100 million elements? That's 100 times as slow as 17.5 hours. Now what are we talking about? 74 days. Right? What if we went up to 1 billion? How long would it take for my little old Mac here to compute that? And by the way, before we go on, is 1 billion large? No. Right? That doesn't even get into, that gets into the gigabyte range, right? It's not even terabytes. Routinely, your computer is doing more than this on a daily basis, on an hourly basis, on a second by second basis. So 1 billion, what do you think? 20 plus years. just a bit off, right? What about the linear behavior? Same here. All right. So same numbers is what I mean. By the way, I did a linear regression on it too, and again, I can't even graph it because it's basically flat. Right? Those coefficients are so small. The growth rate with respect to linear versus quadratic is so much different that it's a flat graph here. Right? But what about the linear behavior? What if I went from to 10 million elements? Well, what I'm going to do is I'm going to go ahead and give up on this experiment here. By the way, I didn't do it. I set up the experiment to get that graph, and then I let it run overnight. I wasn't going to sit around for several hours for all of those data points. So let's go ahead and go back over here, and let's change this to the efficient version. And get rid of the inefficient version. Again, we're taking our paint can with us. Let's go back over here to the demo to see it actually run. This was 100,000 elements, 0.013 seconds. If I go up to 1,000,000, it should take 0.13 seconds, thereabouts. Not even that much. If I ran this multiple times, of course, I would take an average. What if I went up to how many is that now? 10 million. 10 million. That's what we're predicting over here, right? Less than 1 second, right? So, say less than 1 second. Versus, how much was it up here? 18 hours, right? And as we grow larger and larger, the difference between these two time scales becomes way more apparent. 100 million, about 10 seconds. In fact, we can run that one, 100 million, and we'll just let it run there while I tell you what 1 billion would look like. There, at least according to the experiment that I did at the time, it would take about 2 minutes. And this progression here makes sense. If it took about 1 second, or nearly 1 second, then 10 times slower by increasing it from 10 million to 100 million is going to be about 10 seconds. 10 seconds, 10 times as big, 10 times slower, is going to be about 100 seconds or about 2 minutes. Right? And you can see here, oh wow, it was this, how many was this? 100 million? 1 billion? Should only take about less than 10 seconds according to these experiments here. Right? Now I'm wondering what the hell did I run this on, because my computer is running fabulously today. This is much better than it was when I ran these experiments originally. And I've got like a whole bunch of things open, so I have no idea why it's working so well today. By the way, can I go, while we're waiting for this, can I go up to 10 billion? Won't even compile. Why? Because it's an integer, right? If I change that to a long, I could, right? And then I'm risking too much memory or whatever, but that's been more than 10 seconds. Oh, it wasn't? Okay. All right, well, we'll let that go and go on here. All right. So hopefully that was a good motivating introduction that these things matter, right? Oftentimes when in a computer science curriculum, when they talk about algorithms, algorithm analysis, they just leave it at big O analysis and that's it. But I like to give you this kind of a demonstration because, you know, these things matter, right? That you cannot, in the real world, if you go out and operate on real data, you cannot have even a quadratic algorithm and think that it's feasible. You need to look for the most efficient possible solutions. The most efficient, of course, being, well, constant, something that doesn't take any time at all. For example, an array-based list. If you want to jump to a location immediately, all you have to do is compute the memory offset and you're there. You don't have to traverse. Right? So your choice of data structures and algorithms highly affects how performant your code ends up being. And in case you think that this is a made-up example, it's not. This example I found in in fact, a couple of systems over the years where they blindly use an index-based find method on any old list. And if they ever put in, and it never came up because all their data was small. They never had a list more than 1,000 elements, right? Who cares? It's good enough, right? The second that oh wow, it died. Why? Oh, out of memory. Oh well. They can't even do that. But anyway, the Java virtual machine ran out of memory. I could have given it more, but I won't do that right now. Right? I guess it never actually even loaded up the stuff, did it? Did it say done loading data? It never said that, so it got stuck here even populating the linked list. Oh well. But anyway, so these numbers are about accurate, or at least the takeaway here is that their growth rate is accurate, right? If you've got a quadratic algorithm here, then no, you're resigning yourself to 20 plus years of computation time. Versus linear behavior, oh wow, that's way better. How do we recognize when that algorithm is going to suck because it's quadratic, or even worse, it's exponential or something like that, versus yes, that algorithm will probably work well on all inputs, right? We need a formal introduction and a formal framework in order to start doing that kind of stuff. So, introduction. It should be clear that programs, algorithms, require computational resources. So, give me one resource, one obvious resource. Memory, okay, memory. We just ran out of some, right? What else? What was I measuring just now? Time, right? CPU cycles, right? Physical time, etc. What else though? Think about your phone. What's the bottleneck on your phone? Phones are fast. Most phones are fast enough, right? I've got a $200 Samsung that's now 3 or 4 years old, and it's fast enough for anything that I want to do, right? But what is its real bottleneck? What's the most annoying thing about your phone? Battery, right? The power consumption. Would you trade, or so suppose that you need to upgrade and you want to go to the next generation of phone. And you have two choices. You could have a phone that's twice as fast or whose battery lasts twice as long. Which one are you going to go with? Battery, right? Because it's fast enough for everything that I do. I'm not running Halo on my phone, right? Unless you're, does anybody do that? No, okay, exactly, right? What's another resource that computers use? Okay, networking, network, bandwidth, or throughput. Throughput, there we go. All right. That might end up being you could have the fastest computer in the world. If you have a terrible connection, it doesn't really matter. Your CPU is just sitting there idle all the time, waiting for data to come in order to process it. All right. What's another one? So think about, you might not have done any hardware stuff yet, but you will eventually design circuits. Circuitry, what resources are required there? Maybe we don't know that yet. Gates, number of gates or wires in a circuit. Right? If you can design an equivalent circuit with half as many gates, that's half the power consumption. That also translates maybe to twice as quick because for gates to power up or power down, that requires some amount of time, right? And so if you have half as many, then you have half as much time to actually compute something using that circuit, right? Or another one would be idleness, right? Utilization. Again, you can buy hardware to create a server farm that will serve 100,000 people. Okay, what if your customer base is only 1,000 people? Why'd you buy so much hardware, right? It's just sitting there, taking power, not doing anything. Right? It's idle, right? Utilization is low. Instead, what should you do? Well, you should buy something. You should rent server space from Amazon Web Services or Google or somebody like that. Now your utilization doesn't matter at all, right? You can use as much as you want. When it's idle, somebody else uses those actual physical machines. Virtualization takes us to another level where you can have one machine one physical machine, but you can have several different virtual machines sitting on top of it. And on top of that, you can have Docker instances. So you can have virtualization of your actual, user base or whatever, right? And now you only need one machine to serve, 10 virtual machines, right? And now 10 different organizations don't have to buy a server each. They only have to buy one server, and then they get a time slice, 1/10 of the time slice, 1/10 of the price, right? The above are extremely important engineering considerations. When you're actually designing a system, yes, the time, the utilization, the power consumption, all of these things do matter, right? But we don't want to analyze an algorithm just in one context. Here's an algorithm, right? Well, okay, on this system it has very, very good power consumption. But when I move it over to a different system with a different, architecture or whatever, the power consumption is really, really bad. That is definitely an engineering problem, but from the demonstration, do we care about that? That's just a constant sitting out front, A, B, and C. Who cares? What we want to know is, how does our algorithm behave as the input size grows, right? If we have a list of size 1,000 and then we go to a list of size 1,000,000, how much better is it? Well, power consumption, yeah, okay. Memory, yeah, okay. But I want a universal, abstract framework for analyzing these things, right? So from a theoretical perspective, we need an abstract notion of resource that is not tied to a particular machine, right? Why? We want to analyze algorithms from an abstract perspective. Because in the abstract, it does actually translate at the end of the day to all of these engineering considerations. If you have a linear algorithm versus a quadratic algorithm, yes, there's going to be an order of magnitude less power consumption. There's going to be an order of magnitude less memory being used, right? So as long as we are able to analyze it from an abstract perspective, that's going to be sufficient in order to get started, right? What matters is the performance of an algorithm with respect to its input size, not any particular machine, language, architecture, etc. Right? We are interested in the growth rate of the resources consumed by the algorithm. Is it linear? Is it quadratic? Is it exponential? Right? Is it constant, in which case it doesn't matter, right? It is a constant time algorithm. It doesn't matter if the input size is very small or very large. It runs about the same on all of those inputs, right? Algorithms are independent of the hardware they are run on, right? Think about this from a historical perspective. Euclid's GCD algorithm is over 2,300 years old, right? GCD, greatest common divisor. So the greatest common divisor is, you divide one by the other until you get down to a common divisor, and then it's the greatest common divisor. An example would be 60 and 26. Oh no, let's go with 60 and 52. What's the GCD of 60 and 52? I'll ask Wolfram Alpha then. GCD of 60 and 52. Should be 4, right? Because that's what I was thinking of in my head. What is 4? 4 divides 60. 4 goes into 60 15 times. 4 goes into 52 13 times. Therefore, it's its greatest common divisor. And there's no divisor larger than 4 that divides both of those things. Euclid came up with an algorithm for doing this 2,300 years ago. And he was probably doing it on, papyrus or something like that, right? They didn't have computers back then. Does that mean that the advent of modern computers means that Euclid's algorithm is so much more efficient now 2,300 years later? Nope. If you were to do it on a piece of paper, you would do exactly the same number of operations that a computer does. It's just that doing it on paper, one operation takes a whole of a lot more time than one operation in a computer. We don't want our performance to depend on the hardware that we're running it on. That hardware could be an actual modern computer, or it could be a piece of paper, right, from 2,300 years ago. The algorithms predate the modern computer by thousands of years. Right? An algorithm is just a process, a specified list of how to of doing things, basically. Algorithms do not suddenly become efficient because you upgrade your hardware. And I would count going from paper to computer as an upgrade in your hardware, right? Operations, or individual operations is what I should say. Individual operations become faster and more efficient, but the number of operations remains the same. Right? The rate of growth of an algorithm remains invariant, right? Regardless of the hardware. Right? So the idea here is that larger inputs lead to slower performance. Right? Slower performance means more resources, etc. Right? So what we need is a framework, a formal framework for describing an algorithm and its efficiency. So to do the first part, to actually describe an algorithm, we use what's called pseudo code. Right? So what is pseudo code? Well, code is code, but what does pseudo mean? Fake, right? False, right? Pseudo code is false code. An algorithm, formally, is actually not formally, an unambiguous sequence of instructions for solving a problem. Okay? That's the dictionary definition, which I would call an informal definition. If you were to ask, a grade schooler, what is an algorithm? Right? And you gave, they would come up with something like this. Or if you just asked a group of people outside of computer science, what is an algorithm? Hopefully they would know. If they didn't, then I don't know what an algorithm is. But hopefully they would have at least an intuitive sense of what it is. It's an unambiguous sequence of instructions for solving a problem. Okay? That's the dictionary definition. That's not the formal mathematical definition. The formal mathematical definition, at least one of them, is a Turing machine. A Turing machine is a mathematical construct that describes a finite state machine with an input tape and an output tape, or a work tape, et cetera, et cetera. We're not going to get into that. Okay, but that's the formal mathematical definition of what an algorithm is. And whether or not you accept that is called the Church-Turing thesis. Right? You could come up with an alternative mathematical definition for what an algorithm is, and people have done that, lambda calculus, but it can be shown that this mathematical definition is equivalent to this mathematical definition over here. Because anything you can compute over here, you can compute over here, and vice versa. Right? So there are several different notions of what an algorithm means mathematically. That, again, we won't get into. An algorithm is not a Java program. It is not a method. It is not a function. It is not a snippet of code. Right? All of those things mean that we are in the computing world. Go back 2,300 years ago to Euclid. Euclid wouldn't know what the hell is Java, right? That's a place over in another country, right? What's a method? What's a function? What's a snippet of code? Wouldn't know any of that stuff, right? So what we need is all of that stuff is our modern notions. What we need is a good way of describing an algorithm, right? Good pseudocode is a way of describing an algorithm. It makes use of English, plain English, when appropriate. It makes good use of mathematical notation, right? It doesn't have any language-specific constructs. So, for example, most of the languages that we've done so far, you end everything with a semicolon. You put square brackets everywhere, or curly brackets to denote code blocks. We're not going to do that. It gives the essential details of an algorithm while omitting any unnecessary details. Right? So it's going to be more descriptive here. Unnecessary. It's going to be more descriptive here to actually write some pseudocode. So for example, let's find the maximum element in a collection. Okay. For that, I'm going to go over to my iPad here because I don't want to type at all. Typing puts me in the mood for writing code, right? All right, there we go. Typing means that I'll start writing something that looks very Python-esque, right? And I don't want to do that. I don't want to get into that trap. So I'm going to use plain old handwriting here to describe an algorithm for finding the maximum element in a collection. What I'm going to do is, sorry, I'm not over here. There we go. What I'm going to do is I'm going to label the input and I'm going to label the output to start. So input, a collection, A equals A1, A2, dot, 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 AN of elements. Right? So did I say that this was a list? Did I say that this was a set? Did I say that this was a linked list, an array? No. I kept it general and generic. It's a collection of stuff. I've used mathematical notation here. This is set notation. Using these curly brackets right here, that's going to denote, it is technically denoting a set, but it's okay. It can, sets can be unordered, ordered. You do use slightly different notation in math, but this is good enough notation here. What else have I done? I've given the set, the collection a name, A. I've given each individual element a name, A1, A2, A3, dot, dot, dot. And I've also told you what? The size of the set, or the size of the collection. Did I say what each one of these individuals was? That it was an integer, a double, a string, a bank account? No. I kept it general, elements. Okay? My output is going to be the element A sub m in A of maximum value, maximal value. Right? AM, I just gave it a name. So help me out here. If you were writing this in Java, of course, what would you do? For int I equals 0, I is less than n, I plus plus, right? And then get the ith element and do blah, 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 right? We're not going to write a formal for loop that does this, that has those three constructs, the initialization, the continuation or termination condition, and the increment, right? That's code. I'm going to try to use plain old English here, right? For each element, AI in A. Now, if you have some discrete math background, then you might be more comfortable with that notation right there. If not, I'll go ahead and keep it as plain English like this. A sub I in A. Sometimes I like putting colons there. That's getting a little bit too close to Python for me, though. I'm not in the mood for it. Let's go ahead and get rid of it. Superfluous notation, doesn't matter. But I am going to use the indentation to indicate that a block, initially at least, that a block goes from here to here. So for each element in A, what do I need to do? Here's A sub I. Is it larger than the one I've found so far? If A sub I is larger than the one I've found so far, I need a name, right? That's why I left myself some room up here. Right? I need to start somewhere. Where should I start? Okay. The first one. Right? And that'll be my maximum. M stands for maximum, right? Oh, what's that arrow there? Take this thing and put it into this thing over here, right? If I were doing code, what would that look like? AM equals A sub 1 or A sub 0. Another thing that I didn't highlight, do I start at 0? No, that's a computer thing, not a math thing. So I'm not going to write it like that. Instead, I write this left arrow. Some programming languages actually do that. I think that Haskell allows you to use a less than and then a hyphen. And what does that look like? It looks like a left arrow, right? This is my left arrow here, right? It's the assignment operator. Not all programming languages use the equal sign as an assignment operator. Maple is an example. And maybe even Fortran or COBOL or something like that uses a colon equals. In fact, it's considered a huge mistake to have used a single equal sign as an assignment operator when it already had an established meaning of that we use equals equals for, right? I would argue that it was a mistake as well because far too many beginning programmers think equals, okay, that means that A is equal to B, right? And it's algebra. It's not algebra, it's coding, right? But this is much clearer, right? Take the thing over here and put it into the variable over here. Okay, so if it is greater than what I've found so far, then what should I do? Update that. Ooh, I like that. What did I do? I took a vertical line to denote a code block. So I did indentation, but I also took this vertical line here to indicate that this code block begins up here and goes all the way down and ends down here. Right? That's actually a LaTeX thing. I like this style a lot better than square bracket or curly brackets here, because there is no way that you will ever get be able to type that out. Right? That screams to me right there pseudo code. Right? And so if you're doing this by hand, of course, like I am, I would use something like this. Okay? All right. So at the end of this for loop, I have the maximum value. Do I return A sub m? That sounds way too codey to me. What do I have up here? I have input and I have output. So let's output A sub m. And it conforms to this contract that I wrote up here. The element A sub m and m of maximal value. Did I say how I was comparing these things? I kind of treated them like numbers, but I didn't say, what if they're bank accounts? The one with the largest balance, the one with the largest interest rate, the one with the largest last name of its owner, right? Those are all engineering considerations. Those are all coding considerations, not pseudocode considerations. It's very, very nice pseudocode here. There is no way that you could actually, so the whole point of pseudocode is to take the generic description of the algorithm, and then once you have that generic description, you can always translate it to Java. You can translate it to Python. You can translate it to C. You can translate it to an actual programming language, right? But what you've done is you've solved this problem of, searching, getting the maximum element here. You've solved it for any possible programming language. You've just described a general process for searching, and it's basically linear search. Right? Okay. So back to our, I don't need that anymore. Back to our notes over here. Note, there are no rules for good pseudocode, only guidelines. Why? What if there were rules? What if I gave you a set of rules that your pseudocode has to look like this? I just wrote a programming language. Exactly. What is Java? It is a set of syntax rules for describing an algorithm, right? It's code. It's no longer pseudocode, right? So there are no rules for good pseudocode, only guidelines, right? Adopt any style you like. Keep it consistent, right? And like I did here with this handwritten version, I did it with the handwritten version because, I did this style here because if you use a package called algorithm2e in the LaTeX language, LaTeX typesetting language, it'll look something like this. At least I've got it set up to look like this. And unfortunately there are hard and fast rules for typing out LaTeX, so you've got yourself an actual code there. But it comes out looking something like this when it gets typeset. Okay. All right. Once we've got a way to describe an algorithm using pseudocode, now what we need is a framework to analyze the algorithm. And for this, I'm going to give you basically a 5-step process. I have no idea. It might be from Leviton. There are several textbooks that have a general like 4-step process, 3-step process, or something like that. I like to expand it out into 5 steps so that you don't lose the forest for the trees. So I'm going to identify the input. That's the first step. And in case you think that that's simple, it is generally, but also there are some algorithms with multiple inputs. Euclid's GCD algorithm has 2 integers as input. You could have linear search, where you have an entire collection and a key that you're searching for, technically 2 inputs. The collection, that has n elements, so is the input n elements? No, it's just 1, right? It's just the 1 collection. Because in the second step, you identify the input size. And usually you use n here to denote the input size. When we graph things, n is discrete, right? X is not discrete. X, if you were looking at this as an x and y axis, you'd get confused and say, oh, x, well, you can have 1.5 on that x-axis, right? Is there such a thing as an input size of 1.5 elements? No. It's going to be discrete. And that's why we like to focus on discrete mathematics in computer science. And forget calculus. Nobody uses it. Right? Everything's discrete. And by the way, talk to a physicist, and they'll let you in on the dirty little secret that the universe is also discrete, right? Why? Is energy infinitely divisible? No, you get down to a quantum or quanta of energy, right? Planck's constant, where energy goes from one level to another level, and there's no in between at all, right? When it gets down on such a small scale. So the universe is in fact discrete. You identify the elementary operation. The elementary operation could be the most common or the most expensive operation in your algorithm. There could be a choice, a choice of several different operations. You need to be a little bit judicious about which one you choose. All right. 4, you determine how many times the elementary operation is executed with respect to the input size. Right? In other words, this gives you a function. Like we did with the demonstration at the top, we came up with a quadratic function. We came up with a linear function. Once we've got those functions, then we throw out all the constants. We throw out all of the lower order terms. And in step 5, we characterize the algorithm's behavior, that is growth rate, using big O analysis. Right? And like I said, a lot of folks tend to focus just on step 5. and overly focus on step 5. The other 4 steps are just as important, okay, including the first step, the easiest step of identifying the input side, or the input, right? So generally, this is given as part of the pseudocode, right? Pseudocode, right? If you write good pseudocode, you've got input, you've got output. There it is. There's the input. But in some cases, you may have multiple choices. In some cases, the choice may not be clear, right? In general, you only want to focus on one input, right? So, examples. For example, linear search has 2 inputs, a collection and a single key element. Right? Which one should we focus on there? Which one makes more sense? Which one grows? So I want to do a linear search on an array or a collection of 1 million elements, and I want to search it for 5, the element 5 over here. Versus I want to search another collection of 10 billion elements, and I still want to search for 5. Is there going to be a difference in performance between those two? Yeah? Is there a difference in the number of keys? There's just one key, right? What's the real difference? The size of the collection, right? Focus on the size of the collection. Right. Another example, Euclid's GCD algorithm has 2 integer inputs. Right? So, without loss of generality, W log is what we usually do in math. Without loss of generality, focus only on one, the larger input. Right? So if you've got 52 and 60, well, my input is going to be 60, the larger one. Because if the number of operations is going to be proportional to the input size, then I'm going to take the one that's larger. Right? To really separate those two ideas, you want to find the GCD of a 10,000 digit number and a 5-digit number, right? Which one of those should you focus on? The larger one, because they're going to take more operations to cut that number down until you get down to the GCD, right? Etc. Right? Those are just 2 examples that I'm going to give you. The second, well, are there any others? No, otherwise it's just obvious. If you're going to sort a collection, here you go. Here's the collection. That's my input, right? Whatever you say on the box in your input up here, that's what your input is. Right? So it's not that difficult for step 1, but it is important. You identify the input size as step 2. Right? It's subtle, but important, and maybe tricky. Right? So for example, if your input is a collection, then the size is the number of elements in that collection. And that's why we like to label those, that's why I like to label these a collection A, and it has A1 through AN. That already encodes how big it is. It encodes the input, A, and it encodes the input size, N. There are N elements in that collection. Okay. Say an image, right? Has height and width, height and width, right? So what could be one possible input size here? Let's give these names. Let's give this N by M. What's the input size of an N pixel by M pixel image? Okay, so you could go N times M, right? What's another way that you could that's exactly a correct answer, but I want to simplify this, right? That's 2 variables. let's cut 2 variables down to just 1 variable. Otherwise, what's my function going to look like? It's no longer going to look like t sub n. It's going to look like t sub n and m. I don't like that. Let's keep it simple. Assume n is greater than m, then n times m can be bounded by n squared. I'll put it like that. And that cuts it down to just one variable, n. Right? And if you think that that's cheating, okay, take your widescreen image and pad it out with a bunch of white space, and now it's a perfectly square image, right? And the performance is gonna be no different. Or just simplify it to one dimension, n. Right? I don't care about m. I'll assume that n is large or at least as large as m, and then that's all I'm going to care about. Because whatever answer I get out at the end of the day, I can simply just take a square root of it and get an analysis for the original. Right? What about, and most tricky of all, especially for beginners, is what if it's a single number? A single integer, x. Right? How big is x as an input size? Is it 1? Right? That's usually the answer, right? Is it just 1? So, is there a difference between, let's go back over here, sorry. Is there a difference between 5 and 1,873,472,842? Is there a difference between those two numbers? Hopefully. What if I said I'd give you one or the other in dollars? Is there a difference now? Okay. So this is bigger. All right, this is smaller. We already have an intuitive notion of the input size because 5 is much smaller than this 1.8 billion number here, right? How do we quantify that, though? How do you know that? I wrote it down. How many digits did I write on that one? 1 digit. Okay. How many digits did it take for me to express that number? Was it 10? Thank you. All right. So the number of digits that it required me to express that number was 10-fold difference. All right. So if I had just a number x, I didn't tell you it was 5, I didn't tell you it was 1.8 billion, I told you it was x. How many digits does it take to write down x? No? All right. If I gave it to you the other way, if I gave you a max number of digits, if I say I allowed you to have 1 digit, what's the max number that you can express there? 9. What if I said, okay, I won't be so stingy, you can have 2 digits. What's the maximum number that you can write down now? 99. 999. ... If I gave you d digits, how many? What's the maximum value that you could express? What's the pattern here? 10 to the d minus 1. Okay. Now, the max number, that was just x. I gave you d and you work this way. I'm giving you x and I'm asking you to work that way. All right? So we'll take this value and say that's equal to x, and we need to solve for d. This is where we'll end it here. So x is equal to, at most, 10 to the d minus 1. So help me solve for d now. X plus 1 is equal to 10 to the d. Log base 10, good, of this gets rid of that 10 and gives me d, right? So working backwards here, it's going to be log, and now forget about this this plus 1 here. I don't care about it, right? It's going to be about log base 10 of x. Are computers base 10? No. Computers express numbers how? In base 2, right? So in binary, that would end up being what? Log base 2 of x, right? That's going to be the number of, we call them bits, to express x. And just in case you have a question about that, yes, historically they were called bidgets. Bidgets is a stupid name, so they just shortened it up to bits. Why don't we do that with digits? We should start doing that. We don't call them digits, we call them dits, right? All right, we'll continue there next time.